Welcome to the TWIML AI Podcast. I'm your host, Sam Charrington. Hey, what's up everyone? Unless you're Jared Leto or on the cast of Big Brother Germany, you've undoubtedly seen your world shift dramatically over the last few weeks. For most of us, this is simply uncharted territory. And unfortunately, we aren't quite able to see the finish line just yet. Now more than ever before is the time for us all to lean into our various communities. We encourage you to take this opportunity to connect with your fellow human, albeit virtually. And please know that the TWIML community, which is over 3,500 strong on Slack, is here for you, and we welcome you to join us. Take this chance to join a study group, work on a Kaggle competition, share your thoughts on a paper you're reading. We'd love to hear what you're working on and offer our support. For those who might just need a friendly hello, I'm here for that too. If you're so inclined, feel free to reach out via Twitter, our Slack channel, or just shoot me an email to sam@twimlai.com. Please be safe and take care of your health and that of those around you. Peace and love, and on to the show. All right, everyone, I am here at NeurIPS 2019, and I am with Stefan Lee. Stefan is an assistant professor at Oregon State in the School of Electrical Engineering and Computer Science. Stefan, welcome to the TWIML AI Podcast.
Yeah, thanks for inviting me.
Absolutely. Let's talk a little bit about your background before we dive into some of the many things that you're presenting here at the conference.
Sure. So I did my PhD at Indiana University, and most of my work there was sort of on the core computer vision side. So how do I use computer vision to help scientists do various tasks? Mm-hmm. So a lot of it was replacing what would otherwise be human labeling tasks.
Okay.
I get bored somewhat quickly, so in my postdoc I extended out to vision and language. So I'm thinking about problems where an agent has to reason about visual input and linguistic input. So it has to not only understand the visual content, but it has to express that understanding by creating language or responding to language, things like that.
And is visual question answering one of the tasks that is interesting to you?
Yep. So visual question answering, I've got a number of pieces of work on that topic.
Okay.
There's also things like captioning or doing visual dialogues or multi-round Q&A style dialogues.
Okay.
Yeah.
Cool.
And then lately I've been extending out to tasks that not only have vision and language, but also some form of action. So these are vision and language tasks situated in embodied contexts where an agent has to see and talk and move to accomplish some sort of task.
Mm-hmm. And are the agents that we're referring to here, are they simulated agents? Or?
So mostly they're simulated agents, but some recent work has sort of extended out of the simulator into physical platforms with some surprising success.
Okay. What's an example of a platform that you're using?
For simulation or for the robotic platform?
For the robotics, on the robotic side,
sure.
Are they, what's the kind of dimensionality? How complex are they?
Yeah, so most of the work we've been working on so far has been on this Pi robot platform, which is something that Facebook has recently released, which is this wonderful low-cost robotic platform, Locobot, I think they call it.
Okay.
That has a really nice interface for machine learning practitioners.
Oh, really?
Yeah, so
I have not come across that yet.
It's worth looking at. So it's, you can say from Pi robot, import robot, and then robot go forward 1 meter. And that's sort of the level of the interface. So it's a real machine learning person's robot for things like navigation and grasping.
So here at the conference, you've got a number of presentations that and posters you're involved in. We'll talk about one of them in most detail, ViLBERT, but what are some of the others that you've been focusing on?
Sure. So this year I'm presenting a number of things, like you said. One of them is one of these embodied tasks. Mm-hmm. So it's a work on what's called vision and language navigation, where an agent is sort of spawned in a never-before-seen environment and given a natural language navigation instruction. So something like, go down the hall, turn left at the wolf head, and stop on the third bedroom, the one with the yellow bedspread or something like this. So instructions are this mix of trajectory clues, like go forward and turn left, and
landmarks.
And visual grounding and landmarks, exactly. And then the goal is to have an agent that can reason about all of this while actually following that path in a simulated world.
And what are the priors that the agent's bringing into this environment? Does it already know what a wolf head is, or does it need to figure that out from training?
So it's a tricky question. A lot of vision and language, and we'll touch on this in ViLBERT, sort of starts from a set of pre-trained image features and a set of pre-trained language features. What it doesn't have is a sense of grounding. So it may be able to represent a wolf head visually, and it may understand the word wolf head, but the connection between sort of the visual incarnation of a wolf head and then the term isn't there. And that you expect to learn during the specific task. Though in ViLBERT, the point is that we're trying to pre-train grounding itself.
And so you've got the agent paper.
Yep, and then there's ViLBERT, and then I'm also giving a talk at a workshop on emergent communication. So if you have agents that interact to perform some task, and you want them to share information between each other or communicate, how could you make that communication protocol more interpretable to humans? And one way to do that is to make them actually use sort of discrete symbols, so something that looks like a word, more or less, but doesn't necessarily have that meaning. And then the talk is about how do we make these communication protocols more interpretable.
Now, this whole field was kind of, I don't know if popularized is the right word, or villainized a few years ago with the Facebook, those two agents that were said to have developed their own coded language. Similar kind of vein of research here?
Except for the fact that we want to understand what the code is.
Right.
That was this Deal or No Deal paper.
Right.
It had some similar goals.
And so it's, in a sense, kind of merging the field or the desire for explainability into this emergent communication work.
And it, if you're thinking about building an agent that eventually will work with a human, communication ends up being a big part of that. Right? That's how we organize ourselves. So making sure that we can understand what the agent is saying and that the agent can understand what we're saying is sort of one of the goals of my research.
But not constrained necessarily by English.
Not necessarily.
Allowing the agent to come up with its own stuff.
If we can map it back to some space that has human-like structure, that would be fine, right? So rather than having a unique word for the concept of red ball, we'd prefer the agent to have a word for red that modifies a word for ball. So even if it's not English, it's something we can map back to a way that we understand how language works.
And so ViLBERT, what's ViLBERT all about?
So I hinted on this a little bit ago, but ViLBERT's about learning the associations between the visual incarnation of a concept and the linguistic incarnation of a concept. And this is sort of tricky because most people instantly hallucinate the visual part of something whenever they hear the other word. Right? So when I said wolf head, I assume a lot of people immediately thought of like Game of Thrones type of things. And there was some visual concept that got brought to mind. But the machines don't sort of automatically have this, right? You can learn language and just in a linguistic context. And in fact, that's what most of natural language processing does, is just learn it based on its association with other words. Likewise, on the visual side, you're just sort of learning to represent some sparse set of classes, and those classes often relate to specific nouns, but they don't have a sense of closeness, right? So there's no idea that the feature for a cat should be close to the feature for a tiger because they're related linguistically or in certain taxonomies. So the point of ViLBERT is to try to learn these associations between vision and language directly, and this is something we'll usually call a visual grounding of a word.
Okay. And so what's the general approach there? Presumably it involves BERT, transformer models.
The name is not subtle. So if you look at the BERT models and some of the big successes in NLP, it's these large self-supervised tasks. So they take a large language corpus and they learn certain little things to build supervision from unlabeled data. So they'll mask out a few words and have them repredict it based on the other linguistic context, or they'll ask if a sentence follows another sentence in text. And what we do is we find analogs for that in the vision and language space. So there's this data set called conceptual captions that came out recently, which is this massive data set. I think it's on the order of about 3 million image text pairs.
Oh, wow.
Where they just found images online that had alt text. So some human had provided some alternative text for people, usually for people with visual impairment. You might interact with this by mousing over an image, and it produces some text tag. They did some processing on top of that, but it's this sort of Webley supervised data where they scraped all of this down.
And are the images filtered for kind of simple kind of ImageNet types of depictions, or are they just raw whatever's out there on the web?
They're across the board, from everything from Flickr style images to pictures of maps and things like this. So it's pretty broad. But that's sort of where we start as our data source, and we perform similar self-supervised trainings, where we're masking out certain parts of the image just at random, and then asking it to reconstruct those given the rest of the image and the language. And likewise, we're asking, does this sentence match with this image or not? Or we're masking out parts of the language and having it reconstruct from the image and the text. So we're designing this sort of self-supervised multimodal task with this large weakly supervised data source. And what we get at the end is a model that has built some representations that bridge between vision and language. And then we fine-tune that for a wide variety of other tasks.
Now, randomly masking out parts of the image sounds like a very blunt instrument to apply.
Yeah, it is. So part of it is we don't know which parts of the image are being described by the associated alt text. So it's not clear that we should mask out certain regions versus certain other ones. So yeah, it is a blunt instrument, but I think if we were going to be more precise, we would already need to know the grounding, and that's exactly what we're trying to learn.
Yeah, I think the picture that came to mind was doing some kind of object detection in the image and then masking out one or more of the objects. It kind of almost predicates the ImageNet kind of image that I initially asked about, as opposed to more natural scenes. But
well, not only does it predicate that, it's also a good question, how many objects can we detect? Until recently, it was something when the biggest data set for detection was something like 80 or 100 classes. I think OpenImages brought it up to 1,000 or 2,000. But if you actually look at the richness of text, we use all sorts of visual words all the time. I mean, even if you're looking around where we're recording right now, there's lots of objects that you know a word for, you could describe, but it would never show up in a detection challenge, right? So the question is, how do we build groundings for those things? Not just for things we can already detect. Because if we can already detect them, we sort of already have the grounding.
Talk a little bit more about how you've kind of adapted the process for training a BERT-like model, transformer model, to incorporate this additional information.
Yeah, absolutely. So one of the sort of core parts of the BERT model is that it treats this sequence of words, a sentence, sort of as a set of independent inputs, and then does a bunch of self-attention in between to process this. And the actual position of a word in that sequence is just denoted by some positional embedding. So it's really just a set of words with some sequentiality added as a feature representation. And you could think about an image the same way. You could think about an image as a set of bounding boxes, for instance, of just various regions in the image that have been pulled out, and some associated visual feature, and a positional encoding, saying I pulled this box out from over here. So it's just a set. It's an unordered set, in fact. So the actual input API for BERT looks the same in our model for the visual side and the linguistic side. As we're just assuming we have a set of features with some sort of encoding put in. And then we're sort of directly copying over a number of the self-supervised losses that BERT is actually designed for. So masking out parts of the image or asking about alignment between the text and the image. In BERT, it's a sentence and the next sentence, and you're predicting whether one comes after the other. But in our case, it's an image and a sentence, and we're asking, does this align or not? Is this actually a pair from conceptual captions? And then sort of if you're asking about more internal mechanisms, we rely on a co-attentional transformer, which is something we introduce here, but it's been introduced by a number of people sort of simultaneously because it's a sort of intuitive idea that rather than doing self-attention, you're attending one modality based on queries from the other modality. So you're using the language to attend over the image, and then you're taking that sort of pooled image feature back into the language to inform the rest of that computation. And we have those sort of co-attentional layers periodically through this structure.
The result is kind of a jointly trained model that is kind of, it's trained on the relationship. It's not you've kind of trained on some visual stuff and then some language stuff and you found a way to kind of merge them together.
Yeah, I think that's a pretty fair assessment. we aren't training the vision from scratch, so we are sort of starting with some frozen representation, but we are allowing it to learn the association between the two together. Yeah. But it's a very dynamic back and forth process, so it's not just like a direct assignment.
So what's the frozen representation that you're starting from?
We're starting from a faster RCNN trained on visual genome, so it's just sort of a standard practice in the vision and language space.
Okay, and so how is that incorporated into the BERT model?
Sure. So that's the thing that actually outputs these bounding boxes.
Okay.
So it's sort of like your object detection idea, except for that we are not stopping at the classes it actually predicts. We're looking for the associations more broadly. Yeah.
Okay, so the bounding boxes aren't random. They're not driven by this.
Yeah. They're driven by the fast RCN model. You can see
arbitrary more so than random, perhaps,
that's
or not even arbitrary, but it's picking out.
You can also sample from them. So the fast RCN model can produce quite a lot of bounding boxes, and you can sample from them if you'd like to increase the randomness there. If you actually look at some of the bounding boxes that come out, many of them aren't really object aligned.
Okay.
Because if you look at the visual genome data, it's actually fairly noisy. Some of it's very clean, some of it's very noisy. So sometimes you'll have, for instance, an object is like a road very often or something like this. So it doesn't do a great job of honing in on specific objects.
Where does ViLBERT fit into kind of the broader scope of your research? Where do you want it to take you? Is it a means or an end or a little bit of both?
Yeah, I mean, so it's both. Right. So there's a fundamental question of how do we align language and vision.
Right.
And that's the sort of interesting research question. And then why would we want to do that is perhaps a useful follow-up. And there's a number of things that are sort of concrete applications. If you could align vision and text really well, you can train models to do things like VQA or visual question answering, which can help people with visual impairment ask about the world around them and get answers back. Or you could do image captioning to provide descriptions of what someone would be seeing if they didn't have the same visual impairment.
Yeah. And so the idea is that someone could take this ViLBERT model off the shelf and kind of a la transfer learning, just drop it into their application, and what would the inputs be and what are the outputs?
Yeah. So in our case, the inputs are sort of the image features that they're looking at, and then some sort of text query. So we transfer
image features, meaning
the bounding boxes extracted from some model.
Okay.
Yeah. So since the ViLBERT paper, we've applied it to something on the order of 12 different vision and language tasks.
Okay.
So you can pre-train this and then use it as a base to perform fairly well, fairly quickly on a wide range of these visual and language reasoning tasks. So the inputs, some bounding boxes and some text. So let's say I was doing question answering. I would take my image and I would extract these bounding boxes and feed it in, and then I'd feed my question as the text. And I can train an output that just predicts one of some set of answers. And that trains quickly and it trains well, rather than training it from scratch on this data set.
And so you can train it, you can kind of fine tune for specific task types. Presumably you can also fine tune it with specific types of data or kind of data language relationships.
Yep.
How might that work?
Yeah, so this is actually what comes up often in these tasks, right? So ViLBERT's pre-trained on this huge set from conceptual captions that covers, like we talked about earlier, quite a few things. But if you go to something like VQA, which is based off COCO, there's 80 major object categories, and the images are all things people were proud enough to put on Flickr, so that they could eventually get downloaded. So that's a much more constrained image set. But when you're fine-tuning the whole of ViLBERT, and you are feeding in those images and the associated questions, so it can fine-tune.
Got it. So you're kind of doing both at the same time. You're fine-tuning the visual data set, but also the for the specific task that you're asking it to do.
Yep, that's exactly right.
Okay, interesting. And so, kind of going back to the previous question, where does this lead, do you think, from the broader perspective of kind of visual, kind of this integration between visual and language tasks? Yeah,
so I think the grounding problem itself could use sort of more attention. We've been very task-driven as a community, and we're learning sort of myopic groundings, right? So if I train a model for VQA, It understands what Cocoa images look like, and it understands what questions are. Or likewise, if I do a captioning model, sometimes this is even more shocking. You've trained a model to caption Cocoa images. And Cocoa images have a really small set of classes. For instance, one example that I like to show from a recent paper is they don't have any guns. So if we've fed this caption trained on Cocoa with an image of a man in a red hat with a red shirt holding a shotgun. And the caption is a man in a red hat and a red shirt holding a baseball bat.
Okay.
Because he's wearing what looks like a baseball uniform, and he's got something in his hands. Might as well be a baseball bat. And if we talk back to these potential applications of helping people with visual impairment, that kind of mistake doesn't seem justifiable.
Yeah, there was a tweet going around just yesterday or the day before where someone passed a chart into a captioning system, and it was like a chart with like three trend lines or three data sets that were kind of diverging, and it was like something with two scissors.
yeah. So there's that whole side of things. There's this other paper that I recently did with co-author Peter Anderson called NoCaps, which is novel object captioning at scale, and it addresses these sort of problems where how do I caption objects that maybe I've never heard talked about before. So I don't have linguistic data about shotguns, for instance, but I might have an object detector that can tell me that that object exists. And then how do I incorporate that into language descriptions?
Tell me more about that process. How does that work?
How does that work? So that's one of the open questions. So we presented a data set and ran some initial baselines from techniques that had sort of already been floating around on this.
Did you also propose a model that performs well on the task?
Not in that paper.
Okay.
So not yet.
Coming soon. Potentially.
But the way it typically works is the model will consider regions in the image as potential words that it could use in its output. So even if it doesn't really know what the right language for that specific part of the image is, it might recognize that that's an important thing to talk about and want to try to put it into the caption wholesale. And then you rely on the object detector to tell you what that image
Meaning a man in a red hat with some object that I can't identify that seems important?
A man with a red hat holding a that, where that is the image region that contains the gun in this case. And then you rely on object detectors to tell you, or image classifiers to tell you what that image patch actually was to some subset of already defined things. So basically it's saying, if I already know how to use language to describe the world, but I don't know specific objects, it seems silly that I should have to go collect new descriptions that contain that object. Right? You know how to talk, but you may not know what a widget is. But if I point you to a widget, you can then talk about the widget. You just need that first grounding. So this line of work is really about, given that grounding, how do you incorporate it into language models or how you actually talk?
And it likewise seems silly to pick some other random object that probably isn't this thing and stick it in its place.
Confidence estimation is an open problem in this space. Does the model know it's not a baseball bat, or does it really think it is? It's something that needs to be explored if we're going to actually deploy these things.
His other thoughts on kind of interesting challenges in this visual language domain, or the grounding problem in particular?
I'll use the question as an opportunity to talk about some other recent work that I'm excited about. So for a long time in the community, grounding has been on static images. But there's actually a lot of concepts that rely on motion, that rely on interaction to ground. I don't know if I could give you a photo and you could tell me it looks like people are talking, but they could just be sitting there quietly as well, right? It's interaction that actually sort of tells you what's going on. So lately I've been moving...
Are we primarily in this, or definitionally talking about kind of verb concepts as opposed to noun concepts, or... is it independent of that particular distinction?
I think that's a fine generality. I think that's a fine way to understand it in general. Though some verb concepts can be learned from static images. For instance, like jumping. We sort of defies gravity, so we know what they're roughly doing. Though actually, jumping versus falling that nuance doesn't really get captured very easily for a lot of images. So I've been interested in settings where agents have to demonstrate their visual and linguistic understanding in simulated environments by acting. Mm-hmm. This was sort of like the violin stuff I talked about earlier, the first work. But there's also things like if I drop an agent in an unseen environment and I ask them a question, what color is the car? How does an agent navigate, see the car, know that it now has enough information to answer, and then offer up an answer in return? Mm-hmm. So these sort of problems are things that I'm increasingly interested in.
Is the problem there, as you've framed it up, passing a model a sequence of images and having it identify or either caption or identify an action or something else? Or is it more the latter thing that you described seemed different, like the agent navigating the environment, et cetera?
What you described sounds a lot like what video captioning or video question answering would be. What I'm much more interested in is sort of situations where there's active perception. Mm-hmm. So embodiment of some kind. So when I ask what color is the car, if the agent starts in a bedroom, it needs to understand that cars are outside. Mm-hmm. It needs to get into the hallway because it knows hallways tend to lead to outside doors. Right? It shouldn't go to the bathroom attached to the bedroom. There's no outside doors there.
Right.
So it has to sort of start reasoning about structural priors in the world and navigating according to those to actually decide and output an answer in the end. Mm-hmm. So it's more about controlling the agent towards a goal that's specified in natural language. Mm-hmm.
And do you have existing data sets that will allow you to get there, or is that part of the challenge is coming up with new data sets?
Yeah, so I think data sets are obviously a big driver of progress in machine learning. About a year ago, the team at Georgia Tech, where I was working, output this embodied question answering project, which revolved around this. And then there's also the vision and language navigation task from Peter Anderson, which relies on sort of following instructions in environments, again, by controlling the agent. Mm-hmm. So it's recent, but people are producing these sort of things.
Anything else you want to cover?
No, I think that's fine for right now.
Yeah.
If you have more questions, I'm happy to answer more.
Well, we'll be keeping our eyes peeled. We'll be keeping our eyes peeled for your upcoming publications. Thanks so much, Stefan, for taking the time to chat with us.
Yeah, thanks for having me.
All right, thanks.
All right, everyone, that's our show for today. To learn more about today's guest or any of the topics mentioned in this interview, visit TWIMLAI.com. Of course, if you like what you hear on the podcast, please subscribe, rate, and review the show on your favorite podcatcher. Thanks so much for listening, and catch you next time.